Silicon monoxide. Silicon monoxide is the chemical compound with the formula CO where silicon is present in the oxidation state +2. In the vapor phase, it is a diatomic molecule. It has been detected in stellar objects and has been described as the most common oxide of silicon in the universe. Solid form. When CO gas is cooled rapidly, it condenses to form a brown/black polymeric, glassy material, C-on, which is available commercially and used to deposit films of CO. Glassy C-on is air and moisture sensitive. Oxidation. Its surface readily oxidizes in air at room temperature, giving an CO2 surface layer that protects the material from further oxidation. However, C-on irreversibly disproportionates into CO2 and C in a few hours between 400 deg C and 800 deg C, and very rapidly between 1000 deg C and 1440 deg C, although the reaction does not go to completion. Formation of CO. The first precise report on the formation of CO was in 1887 by the chemist Charles F. Maybury 1850–1927 at the Case School of Applied Science in Cleveland. Maybury claimed that CO formed as an amorphous greenish-yellow substance with a vitreous luster when silica was reduced with charcoal in the absence of metals in an electric furnace. The substance was always found at the interface between the charcoal and silica particles. By investigating some of the chemical properties of the substance, its specific gravity, and a combustion analysis, Maybury deduced that the substance must be CO. The equation representing the partial chemical reduction of CO2 with C can be represented as CO2 plus C equals CO plus CO. Complete reduction of CO2 with twice the amount of carbon yields elemental silicon and twice the amount of carbon monoxide. In 1890, the German chemist Clemens Winkler, the discoverer of germanium, was the first to attempt to synthesize CO by heating silicon dioxide with silicon in a combustion furnace. CO2 plus C equals 2CO. However, Winkler was not able to produce the monoxide since the temperature of the mixture was only around 1000 deg C. The experiment was repeated in 1905 by Henry Noel Potter 1869–1942, a Westinghouse engineer. Using an electric furnace, Potter was able to attain a temperature of 1700 deg C and observe the generation of CO. Potter also investigated the properties and applications of the solid form of CO. Because of the volatility of CO, silica can be removed from ores or minerals by heating them with silicon to produce gaseous CO in this manner. However, due to the difficulties associated with accurately measuring its vapor pressure, and because of the dependency on the specifics of the experimental design, various values have been reported in the literature for the vapor pressure of COG. For the PCO above molten silicon in a quartz CO2 crucible at the melting point of silicon, one study yielded a value of 0.2 atm. For the direct vaporization of pure, amorphous CO solid, 0.1 atm has been reported. For a coating system, at the phase boundary between CO2 and a silicide, 0.1 atm was reported. Silica itself, or refractories containing CO2, can be reduced with H2 or CO at high temperatures, e.g. CO2 plus H2 equals COG plus H2OG. As the CO product volatilizes off is removed, the equilibrium shifts to the right, resulting in the continued consumption of CO2. Based on the dependence of the rate of silica weight loss on the gas flow rate normal to the interface, the rate of this reduction appears to be controlled by convective diffusion or mass transfer from the reacting surface. Gaseous molecular CO. Silicon monoxide molecules have been trapped in an argon matrix cooled by helium. In these conditions, the CO bond length is between 148.9 pm and 151 pm. This bond length is similar to the length of C equals O double bonds, 148 pm in the matrix isolated linear molecule CO equals C equals O, indicative of the absence of a triple bond, as in carbon monoxide. However, The CO triple bond has a calculated bond length of 150 pm and a bond energy of 794 kJ/mol, which are also very close to those reported for CO. The CO double bond structure is, notably, an exception to Lewis' octet rule for molecules composed of the like main group elements, whereas the CO triple bond satisfies this rule. That anomaly notwithstanding, the observation that monomeric CO is short-lived and that CO in oligomers with N equals 2345 are known, all having closed ring structures in which the silicon atoms are connected through bridging oxygen atoms, i.e. each oxygen atom is singly bonded to two silicon atoms, no CC bonds, condensing molecular CO in argon matrix together with fluorine, chlorine or carbonyl sulfide COs, followed by irradiation with light, produces the planar molecules OCF2 with CO distance 148 pm and OCCl2CO 149 pm, and the linear molecule OCSCO 149 pm. Matrix-isolated molecular CO reacts with oxygen atoms generated by microwave discharge to produce molecular CO2, which has a linear structure. When metal atoms such as Na, LPD, Ag, and O are co-deposited with CO, triatomic molecules are produced with linear LCO and PDCO, nonlinear AgCO and OCO, and ring Na-CO structures. Solid polymeric CO. Potter reported CO solid as yellowish-brown in color and as being an electrical and thermal insulator. The solid burns in oxygen and decomposes water with the liberation of hydrogen. It dissolves in warm alkali hydroxides and in hydrofluoric acid. Even though Potter reported the heat of combustion of CO to be 200 to 800 calories higher than that of an equilibrium mixture of C and CO2, which could, arguably, be used as evidence that CO is a unique chemical compound, some studies characterized commercially available solid silicon monoxide materials as an inhomogeneous mixture of amorphous C. Recent spectroscopic studies in a correlation with Potter's reports suggest that commercially available solid silicon monoxide materials cannot be considered as an inhomogeneous mixture of amorphous CO and amorpha. Interstellar CO. Interstellar CO was first reported in 1971 after detection in the giant molecular cloud SGRB2. CO is used as a molecular tracer of shocked gas in protostellar outflows. References